Circular parallel plate capacitor. A metallic circular plate with radius r is fixed to a tabletop. An identical circular plate supported from above by a cable is fixed in place a distance d above the first plate. Assume that d is much smaller than r. The two plates are attached by wires to a battery that supplies voltage V. Part A, what is the tension in the cable? Neglect the weight of the plate. Part B, the upper plate is slowly raised to a new height 2D. Determine the work done by the cable by integrating from D to 2D f of c dz, where f of c is the cable tension when the plates are separated by a distance z. C, compute the energy stored in the electric field before the top plate was raised. D, compute the energy stored in the electric field after the top plate was raised. And part E, is the work done by the cable equal to the change in the stored electrical energy? If not, why not? Okay, so we have these circular plates, radius r. So we have a battery connected between them, and this top plate is at a distance d from the bottom plate, and it's attached to a cable, and it can be raised to a certain height so that the separation between the two plates changes. D is much less than r, and this is our y-axis. Okay. So for part A, we were asked to find the tension in the cable. The electric field that we see in between the plates is the potential difference being applied, V, divided by the separation between the plates, and the electric field points in minus j hat direction according to the figure that I have drawn here. And this is equal to the electric field due to the top plate plus the electric field due to the bottom plate. And I know that these two plates have the same magnitude of the electric field being applied, which is sigma over 2 epsilon 0, remember, using Gauss law for sheet of charge. For example, for the electric field of the bottom plate, applied by the bottom plate, I have V divided by 2D in minus j hat direction, and this is actually equal to the surface charge density sigma divided by 2 epsilon 0 in minus j hat direction. This is basically the sheet of charge electric field that we have found using Gauss law. So we see that the potential difference V divided by 2D should be equal to the charge Q that is stored on this plate divided by the area of the plate, pi r squared, and then we have 2 epsilon 0. The 2's will cancel out, and I will see that the charge that is stored on the bottom plate is magnitude-wise, it is epsilon 0, potential difference V, pi r squared divided by D. So that is the charge stored on these plates. It's this equal amount of charge stored on the top plate. So for the bottom plate, actually, this should be negative. So we would have a minus sign here for the charge being stored. But for the magnitude of the charge, it's going to be the same. So on the y-axis, if I have equilibrium here, the electrical force the top plate will feel should be balanced by the tension. Okay, so the equilibrium condition is that the net force on the y-axis should be 0 according to Newton's laws of motion, and the electric force that we will see for the top plate will be equal to the electric field seen by this plate multiplied by the charge on the plate. What is the electric field seen by that plate? It is the electric field created by the bottom plate. And this must be equal to the tension. Okay, so I see that the tension is equal to, for Q I substitute epsilon 0 V pi r squared over d, and for the electric field I substitute V divided by 2d. So V divided by 2d is the electric field created by the bottom plate, and then I have epsilon 0 V pi r squared divided by d. So this gives me a tension of pi epsilon 0 r squared v squared divided by 2d squared. All right, so that's the tension. And remember that we're neglecting the weight of this plate. So the only force that we're taking into account is this electric force, which is pointing down from the positively charged plate towards the negatively charged plate. And this positively charged plate feels the electric field created by the negatively charged plate. And the attractive force is basically the electric field it feels due to this plate multiplied by the charge on that plate. Now, part B asks me if I raise the top plate, how much is the work done by the cable? All right. So the work done by the cable, and this is also given in the problem statement, is integral d to 2d, because I have assumed that this is on the y-axis, f of y dy. So this will be equal to integral from d to 2d. Now I substitute for the force, the tension, pi epsilon 0 r square v square divided by, when they're at a distance y from each other, 2y square dy, and this will give me pi epsilon 0 r square v squared over 2. The integral of dy over y squared is minus 1 over y, which will be evaluated between d and 2d. So this will give me pi epsilon 0 r squared v squared divided by 2, 1 over d minus 1 over 2d. So that's basically going to give me, for the final work done by this cable, W, pi epsilon 0 r squared v squared divided by 4d. So that's the answer to part B of the problem, because I will have 2d minus d, which is d divided by 2d squared. So that will give me 1 over 2d multiplied by 2, 1 over 4d. So that's the work done by the cable. Okay, so let's move on to part C. Part C was asking the energy stored in the electric field before the top plate was raised Well, what is the capacitance here? Capacitance is equal to epsilon 0. We have air in between the plates, so it is epsilon 0 pi r squared divided by d, and the energy stored in this configuration is 1 over 2 CV squared, and therefore I see that the energy stored in this configuration is epsilon 0 pi r squared v squared divided by 2d. That's the energy stored before it was raised. Now, what is the energy stored? So part D in the electric field after the top plate is raised to a distance 2d. That's what we are doing. So now the new capacitance is epsilon 0 pi r squared divided by the new separation between the plates, which is 2d. Now the energy stored is 1 over 2 c prime v squared. We have the same potential being applied, and therefore the energy stored becomes epsilon 0 pi r squared v squared over 4d. Now part E is asking me about the change in the stored energy. So the change in the stored energy is U2 minus U1. Now you can see this is 1 over 4d, this is 1 over 2d, 1 over 4d minus 1 over 2d. It will give us negative energy, minus epsilon 0 pi r squared v squared over 4d. So I note that while the cable does positive work, you can see here pi epsilon 0 r squared v squared over 4d, the change in the stored energy is negative. So the plates basically lose energy. All right? So that's what I observe. So keeping the potential constant, there is an energy loss to the battery. You can see here, there's an energy loss to the battery. Normally, you would have Q prime is equal to Q, which is the new potential multiplied by C prime, if it was not connected to the battery. And then you would see V prime would be because we have CV is equal to CV prime times C over 2. It would be V prime is equal to 2V. So that's what would happen. But to keep the potential constant, because it is connected to the battery, there is a change, there is a charge transfer. How much is the charge transfer? Charge transfer of Q over 2 from each battery, from each plate to the battery. So to keep the potential constant, this new charge, Q prime, is not equal to Q, but it's equal to Q over 2, so that you would have this potential being kept constant. So the potential here, remember, is Q over C, And what happens to this potential? It is kept constant and the capacitance is reduced. So if the capacitance is reduced to C over 2, that's because C prime is C over 2, then you need to have the charge being reduced to Q over 2. So we need to have a charge transfer from each plate to the battery, which is responsible for this negative change in the potential energy because we're losing charges to the battery. Okay, so for this circular parallel plate capacitor, we have two circular plates, radius r, separated by a distance d. The top plate is connected to a cable, the bottom plate is fixed to the tabletop, and we have a potential difference V between the plates. Electric fields from, according to this figure, points from top to bottom. The top plate feels an electric force, attractive force towards the bottom plate due to the electric field created by that plate, and there's a tension on the cable that balances this force. So the electric field due to the bottom plate is sigma over 2 epsilon 0, which is V divided by potential difference V divided by 2D. The total electric field is V divided by D, but the bottom plate has half of that. And it's pointing towards the bottom plate. And this electric field basically is felt by the top plate. Now V over 2D is the charge density Q over pi r square over 2 epsilon 0 due to the sheet of charge. So we can calculate the charge stored on these plates, the equal and opposite sign. And you can see that the top plate feels electric force Q times electric field due to the bottom, and that is balancing the tension. So we find that the tension is pi epsilon 0 r squared V squared over 2D squared. If we raise this upper plate to a new height 2D slowly, we want to know the work done by the cable. The work done by the cable is the integral of dot product of the force with displacement. The displacement is in j hat direction, the force is in j hat direction, so we have a positive dot product. Integral from d to 2d, tension multiplied by dy gives us the work done, which is positive. There's positive work being done by the cable. If you look at the energy stored in the initial configuration, we have epsilon 0 pi r squared over d, our capacitance, and 1/2 CV squared, the initial energy stored. For the new separation 2D, this energy stored becomes half of the energy stored in the initial configuration. There is a decrease in the energy, which is minus epsilon 0 pi r squared V squared over 4D. So while the cable is doing positive work, there is a loss of energy. The loss of potential energy is due to the fact that we're transferring a total amount of charge Q over 2 from each plate to the battery to keep the potential constant. If we didn't have this requirement, then we would have the potential difference being increased to 2V when they hold the same amount of charge.